For this problem, we have this graph here showing the force exerted on three different objects and their resulting accelerations. We know the mass of the one object, object 2 here, is 0.3 kilograms. And we're asked to use that to find the other two masses. So there's two ways of doing this. The first way, and maybe the slightly easier to understand way, is to look at this graph, and I'm going to pick a point here. And the reason why I'm picking this point is this. I don't know units of number of rubber bands. Okay, I don't know that as a unit of force. What I do know, though, is newtons. And if I know my force in newtons, and I know my acceleration, I can calculate my mass. So I need to use this known mass from object 2 to figure out how much force we have when there's however many rubber bands exerted. So I'm going to use this one point here, 4, 4. What I'm going to say is I know sum of the forces equals ma. So the force we have here is the force of the rubber bands. And for that point there, my acceleration is going to be 4 meters per second. And my mass is going to be that 0.3 that we were given. So I find that the force there is 1.2 newtons. And that was for 4 rubber bands. That means that if I only have one rubber band, my force is going to be 1.2 divided by 4, or 0.3 newtons. So that's the force for one rubber band. So I can actually use that to calculate the mass of object 1. So I'm going to look at object 1. I'm going to pick a point there, and I'm going to say F equals ma. In this case, the only force we have acting on it is the force of the rubber bands. So the sum of my forces is simply the force of the rubber bands in this case. So for that point, I have 2 rubber bands. I know that my force then is going to be 2 times 0.3, because that was the force for a single rubber band. And that's going to be equal to the mass of object 1, which I'll call m1, times my acceleration at that point, which is 5. So I end up getting here 0.6 equals m1 times 0.5. And for my answer, I'm getting a mass here of 1.2 kilograms. Moving on to object 3, same strategy there. Okay, I'm going to pick a point here. In this case, I'm picking that point. Sum of my forces equals ma. So the force I have there now is 5 rubber bands, if I look down at the bottom here, times the force for each one, which is 0.3. That's going to be equal to the mass of the object times its acceleration, which is 2 in that case. So I get 1.5 equals 2m, which means my mass now is 0.75 kilograms. There is an alternate method that we can look at here, and that is using the equation F equals ma. There's another way of doing this problem, and that is, once again, using the equation F equals ma, but thinking about what that relationship shows between those variables and what that would look like on a graph. So let's start with that equation, F equals ma. And if we look at our graph here, we see that the y-axis has a on it, and the x-axis has force. Now, if you remember from our unit on linearization, when we're trying to do that equation matching, I call it, and think about what a graph would look like based off of an equation, we always first isolate the variable that's on the y. So we can say the acceleration is equal to force divided by mass. And then I'm going to further go ahead and isolate what's on the x-axis, which is force, by pulling out any constants. So we can say acceleration equals 1 over mass times the force. And that, okay, allows us to see what would be on the y-axis, what would be on the x-axis, and what the meaning of slope is. And so we have acceleration on the y, force on the x, and our slope then is going to be, and this is a little bit confusing because we have an m for slope and an m for mass, but our slope is going to be equal to 1 over the mass of the object. Okay. So we could use that and get our slopes and look at the ratio of our slopes to be able to get our other masses. Now, I think that's a little bit more complicated of a way of doing it, so I'm not going to work through that entire solution. But just be aware that that is another way that you could do it, just getting you thinking about other ways to solve this. Okay, for this last question, we're asked to explain our reasoning here. And I'm going to just write this down again, the fact that slope is equal to 1 over the mass of the object because that's going to play a role here. So the first response is a larger slope implies a smaller mass. That is true based off of what we know about the slope itself. The next two are about solving it by comparing accelerations. Those are not true. And the last one, a larger slope implies a greater mass. That's also not true because it's actually the opposite. A larger slope implies a smaller mass. So this one would just be that first response there. This next one here, this is one of our ratio ones. So we have a situation where a constant force is applied to a cart, causing it to accelerate 10 meters per second squared. And we want to know what will happen if various aspects of that are changed. So what I'm going to do is I'm going to start with the original situation here and think about my F equals ma. Sum of the forces equals ma. We have some force, just going to say F, that's the force making this object accelerate. The object has some mass, m, and it's accelerating at 10 meters per second squared. So that's my original situation. My new situation for part A, what will the acceleration be if the force is halved? So I can say that's going to be 1/2 F equals ma, okay? And then I'm just going to substitute in, okay, this force here into this equation. And so I can say 1/2 times m times 10 equals ma. My m's cancel out here, and so I find that my acceleration is just 5 meters per second squared, half of my original. Answering to 2 sig figs, it would be 5.0 meters per second squared. Moving on to B here, what will the acceleration be if the object's mass is halved? All right, so I'm going to set this one up again, and I'm going to say now F equals 1/2 m times a. Back from my original situation, I have F was equal to m times 10. So once again, I'm going to take that original equation and sub it in there for F. And so we get m times 10 is equal to 1/2 m times a. M's cancel out. We multiply both sides by 2, and I get that 20 is equal to my acceleration, 20 meters per second squared. Answering to 2 sig figs, this is one of those ones where you have to write a scientific notation to technically answer it as 2 sig figs, so 20 times 10, or 2.0 times 10 to the first. I think, though, it will accept 20, even though it says use 2 sig figs. Moving on to part C, what will the acceleration be if the force and the mass are both halved? Okay, so let's start by setting up our equation for this one. We're going to have 1/2 F is equal to 1/2 m times a. We can actually cancel out these two 1/2s, and we're just left with F is equal to ma. So nothing has really changed, but if we're continuing in our method here, before we had F was equal to our mass times 10. And now we can just substitute in that F once again. So we end up getting m times 10 equals ma. And so our acceleration is 10 meters per second squared. Once again, if we want to be proper with our sig figs, it would be 1.0 times 10 to the first, but I think that it will accept 10 on its own. Lastly, what will the acceleration be if the force is halved and the object's mass is doubled? So we have 1/2 F is equal to 2m times our acceleration. We bring in that original once again, F is equal to m times 10, and we can substitute that in for the F there. And so what I'm left with is 1/2 m times 10 is equal to 2ma. My m's will cancel out here. I'm going to multiply 1/2 by 10, so I get 5 is equal to 2a, which means my acceleration is equal to 2.5 meters per second squared. And that already is to 2 sig figs, so we can just answer 2.5. Moving on to the next one here, we have a situation where two children are fighting over a 200-gram stuffed bear. One children's pulling to the right with a force of 15 newtons. The other is pulling to the left with a force of 17 newtons. I'm just going to real quick draw a free body diagram here. So there's the 200 kilogram bear. One force is going to the right, that's 15 newtons. The other is going to the left, that's 17. So the first two are just conceptual questions. At this instant, can you say what the velocity of the bear is? And forces don't tell us about the velocity of objects. Forces tell us about the acceleration. So if all we know are the forces, the answer is no. We can't say what the velocity is. All right. However, we can say what the acceleration is, because forces, unbalanced forces, lead to accelerations, and we can calculate the amount of acceleration based off of the force. We can't, though, calculate the velocity. For part C here, we're asked to calculate that magnitude of the acceleration. So I'm going to say sum of the forces is equal to mass times acceleration. And I'm going to fill in the forces I know. I have 15 going to the right, plus that negative 17 going back to the left. That's going to be equal to the mass of my object, but I have to be careful because it's 200 grams. We want it in kilograms, so we're dividing by 1,000. Okay, we could write out that conversion, 200 grams times 1,000 grams in 1 kilogram. And that gives us 0.2 kilograms as our mass. And that's what we want to use. That's our standard unit for mass, is kilograms, times our acceleration. So we end up with negative 2 equals 0.2a, which means my acceleration here is going to be 10 meters per second, negative 10 meters per second squared. Two things about going to put my answer in. Number one, it says what is the magnitude? That means we're going to take the positive, and we're going to answer to 2 sig figs. Once again, I think you technically could just write 10, but if you want to be proper and do 2 sig figs, it's 1.0 times 10 to the first. But they should accept an answer of 10 as well. Last question was the direction of the acceleration. Two ways of thinking about this. Number one, we see clearly that there's more force to the left than to the right, and so that means that our acceleration is going to be going left. Or you could look at the fact that before we found the magnitude, when we actually got that answer for our acceleration, it was negative. We set left to be the negative direction, so that means our acceleration is left. Up next, we have a 1,500 kilogram car that's traveling along a straight road at 17 meters per second. And then 2 seconds later, it speeds up to 24 meters per second. And we want to know the magnitude of the net force acting on the car during this time. So the first thing I'm going to do is we have some information here about the velocities and the time. So I'm actually going to set up my kinematics first, because that's going to allow me to find my acceleration, and that's going to ultimately help me find my force. So I have my chart here in terms of kinematics, at least based off of my numbers. I'm starting at a velocity of 17. My final velocity is 24, and that occurs over a period of time, 2 seconds. So to get my acceleration, I can just do my VF equals VI plus AT. So 24 equals 17 plus A times 2. And when I ultimately solve for that, I get an acceleration here of 3.5 meters per second squared. Once I have that, I can get that force. It's asking for the net force. Net force is just another way of saying sum of the forces. So what I'm really solving for is that left side, okay? What is the sum of the forces, or the overall force, or the net force? There's lots of ways of saying it acting on this object. So I'm going to say that my net force is equal to 1,500 times my acceleration, which is 3.5, okay? And that gives me an answer here of 5,250 newtons is my net force. My answer does ask for 2 sig figs, so that would round to 5,300 newtons, although I think they would accept 5,250. Next, we have a situation here with a few different ropes pulling on a ring, and we want to find the magnitude of the tension, or the force, in 2 of the ropes, rope 1 and rope 2. So the first thing that's jumping out at me is I'm going to think about the forces acting on this ring. The ring here is the object, and the ropes ultimately are the forces. So we have a force here from rope 2, a force from rope 1, and this 100 Newton force. Now, one thing that should be jumping out at you is that 100 Newton force is at an angle. So I'm going to break that up into x and y components right off the bat. So my x component is going to be 100 cosine of 30. My y component is going to be 100 sine of 30. Now that I have that, I can go ahead and set up my max and my may. So in the x direction, the forces that I have, I'm going to have this 100 cosine of 30 minus that force from rope 1, which I'm calling F1. You could call it T12 for tension, and that's going to be equal to the mass of the ring, which we don't know, but its acceleration is 0, okay, because that ring is just fixed in place. So that means that F1 is equal to 100 cosine of 30, or 86.6 newtons. And that ends up being my answer to part A. Moving on to part B, I'm going to set up my F equals ma in the y direction now. I'll set that up down here. In the y direction, we have this F2 minus 100 times sine of 30, and that's equal to the mass of the object. Acceleration, once again, is 0 because the ring itself is not moving. And so F2 equals 100 sine of 30, which means that F2 is 50 newtons. And there's my answer to part B. Moving on to this question, we want to find the horizontal and vertical acceleration of an object based off of the forces acting on it. So we, of course, are going to go right to our F equals ma. We already have our forces shown in the diagram. We don't have any at angles, so we don't need to worry about components, so we can just go right to sum of the forces in the x equals max. So in the x direction, we have 4 newtons minus 2 newtons going to the left, and that's going to be equal to our mass, 1.4, times our x acceleration, which is what we're looking for. And so we get 2 equals 1.4 ax, which means that our x acceleration is 1.43 meters per second squared. When we go to put it in, it does say 2 sig figs, so technically it would just be 1.4 meters per second squared. Moving on to our y, sum of the forces in the y. What do we have there? We have 3 going up, plus 1 going down, plus a 2 going down as well. That's equal to 1.4 ay. Alright, so based off of the forces that I have, although yours might be slightly different, I actually get 0 net force acting on the object. That's equal to 1.4 ay, which means that my y acceleration is simply 0 meters per second squared. If we're being careful with our sig figs, I guess it would be 0.0 meters per second squared. Up next, we have a horizontal rope being tied to a 90 kilogram box that's on frictionless ice. And so the rope is going to be pulling on the box, so I'm going to go ahead and set up my free body diagram. Going up, we have the force of the ice supporting the box. Going down, we have the force of Earth, and then we have the force of this rope, which oftentimes is called the tension force. So for our first situation, what is the tension in the rope if the box is at rest? Well, that means that our acceleration is 0. If our acceleration is 0, we don't want any force in the horizontal direction, because if we did have a force, we wouldn't have 0 acceleration. That unbalanced force would lead to an acceleration. So, what is the tension in the rope when the box is at rest? It's just 0 newtons. Moving on to part B, what is the tension in the rope if the box moves at a steady 4.0 meters per second squared? Well, that also represents 0 acceleration. So that also is a force of 0. And this really is a great demonstration of Newton's first law here. Okay? Both the case of being at rest and the case of moving at a constant velocity require no unbalanced force, because both of those cases mean the object is not accelerating. We only need an unbalanced force in order to accelerate. Okay? Whether or not we're moving is irrelevant. Moving on to the last part, what is the tension if we have an acceleration now of 5 meters per second squared? So I'm going to set up my sum of the forces in the x is equal to max. So we just have the force of the rope, okay, that's the only object pulling on it horizontally, equals our mass here, which is 90, times our x acceleration, which is 5. So that means the force of the rope here is going to be 450 newtons. Alright, for this one we have a 600 kilogram steel beam is supported by 2 ropes, shown in the diagram here. We want to calculate the tension in the rope. So the first thing I'm going to do is I'm going to think about my forces. I have one force here from the first rope, F, and one force from the second. So I'm going to call them F1 and F2 to match up with the names of the ropes given. We also have the force of the earth. And if you look, there was a note here that stated that the force of the earth is simply equal to the mass of the object times 9.8. And we'll be talking more about that later, but for now we're just going to use this shortcut here. So the force of the earth in this case is simply going to be 600, which is the mass, times 9.8, which gives me a force of 5,880 newtons. So there's my force of the earth. I'm now going to go ahead and break my angle of forces here into components. All right, so I have F1 sine of 30 is that x component, and that y component is going to be F1 cosine of 30, and same thing for F2, that x component is going to be F2 sine of 30, and the y component is going to be F2 cosine of 30. Now, when I go ahead and set up my F equals ma, I'm going to take advantage of one little trick here, and that is these 2 ropes here are at the same angle. So I'm going to take advantage of symmetry. And what that means is that F1 in this case is equal to F2, and that occurs because the angles are the same. Okay, it's going to be 2 symmetrical angles, and we could go through a mathematical proof of why that's true, but I think it's easier just to know that in this case where it's symmetrical, we're going to say they're equal. And so what that means is when I'm setting up my F equals ma, I'm really only focused on the y direction. The x direction, those 2 forces just cancel out to 0. But I want to get this force of the earth in here. So in the y direction, sum of the forces equals may. I'm going to have F, I'm just going to call it, cosine of 30 plus F cosine of 30 minus that force of the earth, 5,880, equals my mass. And my acceleration is 0 because this beam is just hanging here. So I can say 2 times F cosine of 30 minus 5,880 equals 0. 2 times F cosine of 30 equals 5,880. And I divide both sides by 2 cosine 30. And I find that my force here becomes 3,395 newtons. Okay, now rounded to 2 sig figs, that's just going to be 3,400 newtons as my final answer. All right. The next question, second part of this, the rope can support a maximum tension of 3,200 newtons. Is the rope strong enough to do this job? So the answer here is no. We need 3,400. They only have 3,200. The tension exceeds the maximum value. That other option, the tension of the ropes do not exceed the maximum value, but since they're not vertical, that really has nothing to do with it. That's also not true. We accounted for the fact that the forces are at angles, right? We did that by breaking them into components. We found the actual magnitude, that hypotenuse of the force. So 3,400 is the force. It's more than 3,200 and not enough to support it. Okay, moving on to this next problem here. We have 3 forces acting on an object, and we see the magnitudes there, and we have our diagram over here showing the direction of those 3 forces. And what we want to do is determine the net force by combining the 3 individual forces. Okay. So this one's actually a little bit different in that we're not actually going to use max and may here. We simply want to add up the 3 forces. This is really just a vector addition problem. So what I'm going to do is I'm going to start by breaking my forces into components. So I'm just going to draw them up here. I have F1, which has a magnitude of 4 newtons. and I'm going to break that into components. We know this angle here is 25 degrees, so this side is going to be 4 cosine of 25. This side is going to be 4 sine of 25. And so I find that my x component is 3.63 newtons, and my y component here is going to be 1.69 newtons. I'm also going to take this F2 down here and break that up into x and y components. So F2 is 6 newtons, all right? And so we'll break that into components. So we have our x component here and our y component. There is one slightly different thing here, and that is how our angle is measured. So we actually measured it from the positive x-axis, and so it's a 325 degree angle. So two ways you can deal with this. Number one, you actually can do sine and cosine of that 325 and it will work out okay. But what I usually do is I would just find this angle here. That's kind of what our normal way of doing this is. So since the entire way around is 360, we subtract that 325 and we get that this is just a 35 degree angle. So our x component is going to be 6 cosine of 35. Our y is going to be 6 sine of 35. And so we get that this x component is equal to 4.91 newtons, and my y component is equal to 3.44 newtons. Now that I have that, I can go ahead and I can add up my x and my y components like I would normally do for vector addition. So in the x direction, we have this 3.63 Newton force, plus we have a 4.91 Newton force, minus, we don't want to forget about F3, that 8 Newton force. And so we end up getting a resultant in the x direction of 0.54 newtons. In the y, we're going to add up our y forces. So we're going to have 1.69, okay, that y component of F1, minus 3.44, that y component of F2, and we end up getting an overall y component of negative 1.75 newtons. We're going to put it back together now, so we have our 0.54 in the x, 1.75 newtons in the y, okay, and then our resultant is just that hypotenuse there. So we can do a squared plus b squared equals c squared to get the magnitude, 0.54 squared plus negative 1.75 squared, and that's going to be equal to c squared. So I get that c, my hypotenuse here, is 1.83 newtons. And that is my answer to the magnitude of the resultant force. If we do it to 2 sig figs, it would just be 1.8. Up next, we want to find the angle. So what I'm going to do is I'm going to say that tangent of theta is equal to opposite, which is 1.75, over adjacent, which is 0.54. And I can go ahead and take the inverse tangent of both sides, and I can solve for my angle here. And so I end up getting a theta of 72.9 degrees. Now, it does have this weird thing that specifies, if we go way back up here, it said that we want to measure all angles from the positive x-axis, and we're going to go counterclockwise. So this is how we typically measure angles in math class a lot of the time. So what I just found is that this angle here is 72.9 degrees, but what I really want is that angle there. So 360 minus that 72.9 degrees, and so I end up getting an angle measured from the positive x counterclockwise of 287 degrees. All right, what is the magnitude of the block's acceleration? Okay, well this part's actually not that bad now that I've gotten the first two. Since I know the overall magnitude of the force, I can simply use that to get the overall magnitude of the acceleration. So my overall force was 1.83 actually was our number before we rounded to 2 sig figs. And that's going to be equal to the mass, which is 2, times the acceleration. Okay, so I can go ahead and solve for my acceleration. I get that my acceleration is 0.915 meters per second squared. and I could round that to 2 sig figs. That would be 0.92 meters per second squared. What is the direction? All right, this is an easy one here because whatever the direction of the net force is, that's going to be the direction of the acceleration. So the answer to that is simply going to be the same as part B, 287 degrees. Moving on to my last part, how far will this object move? Remembering that it starts from rest. So I can set up my kinematics, and I can go ahead and solve for this. I know I'm starting from rest, so my initial velocity is 0. My time is 5 seconds, and my acceleration is 0.92 meters per second squared. I'm going to use my delta x equation. That first term goes away because we have 0 initial velocity, so my displacement is simply equal to 1/2 times 0.92, which is my acceleration, times 5 squared. And so when I multiply that out, I end up getting a displacement here of 11.5 meters. Okay, rounded to 2 sig figs, that's just going to give me 12 meters.